Okay, I'll introduce the next speaker, Vyom. He's going to talk to us today about a microwave single-photon detector based on superconducting lambda systems with engineered couplings.
Okay. Yeah. Yeah. Hello, I'm Vyom. I'm a PhD student at Chalmers, and for the next 10 minutes, I would like to pivot this session away from amplifiers and towards another way of detecting low energy radiation, which is photodetection. So this work was done in the group of Simone Gasparinetti at Chalmers University in Sweden, in Gothenburg. And do visit our lab website to check out more cool research that our group is doing. Okay, with that, let's get into our experiment. Okay, so as has been discussed in this session, what is very standard in the field of superconducting circuits is to detect the quadratures of a field after amplification. And yeah, this has been for quite a while now. And what the tool that is missing in the toolbox of circuit QED is a microwave photodetector. While this is quite common at optical frequencies, since single-photon detectors are commercially available. For example, you see here a very famous experiment from Hanbury Brown Twist from very long ago, where they used photomultiplier tubes to detect photons. However, at microwave frequencies, having photomultiplier tubes is quite problematic because the energy of the photons is almost lower by 4 orders of magnitude. So if we do want a photodetector in that regime, we have to solve this. So how do we do that? Well, we can go back to circuit QED as a toolbox for microwave photodetection. And well, we know that it operates at the required frequencies of around gigahertz. And okay, this is not the first time that people have tried building photodetectors with circuit QED systems. The central idea so far has been to map a propagating photon onto a long-lived qubit state, which is then read out using conventional dispersive readout. Okay, so far there have been two main tracks that people have tried to do photodetection in. So one of them has been to put a qubit in a cavity, put it in a superposition state, equal superposition state, and when you have a photon reflecting off the cavity, it imparts a phase onto the qubit, which can then be detected in a Ramsey experiment. Another way that people have tried to do photo detection with superconducting qubits is to have an impedance matched lambda system, where in a combination of drive and dissipation, what you have is a photon absorbed by one of the transitions is deterministically transferred to another transition that can be then read out. So it is this second type of track that we have tried to use, and so we'll get more into that. But before we go ahead, an interesting part of all of these experiments is that the photodetection is QND. So revealing the presence of a photon does not destroy it in any of these experiments, which bodes well for us. All right, so yeah, let's get into an impedance matched lambda system. So what you see here is a 3-level system with some decay rates from the top state to the ground and M state. So if you hook this up to a waveguide or a semi-infinite transmission line, and you send a photon down that transmission line that is resonant with either of these transitions, say for this purpose is with the E to M transition, what happens is the photon absorbed is deterministically transferred to the G state because of the equal decay rates. So this is the result of some interference processes on the 1D transmission line interacting with this lambda system. Now, this has a very simple analog in the field of microwave engineering, where you have a transmission line with a certain characteristic impedance Z0 that is terminated by a load impedance ZL. And if you match these two, so if Z0 is equal to ZL, what you have is that all the radiation propagating down the transmission line is completely absorbed by the load impedance. And this is quite similar to what we will be trying to do. We'll be trying to absorb a propagating photon deterministically and read it out. But how do we do this? So as you can imagine, such systems with equal decay rates from the top state to bottom states, they are not super easy to find in nature. So we have to do something to engineer it. And the way to engineer it has been to use a drive and dissipation on a 4-level system to create such a lambda system in the rotating frame where the decay rates are equalized. Yeah. So now let's get into our device, the way that we will be trying to do this. So here you see our device, and it's made of 2 frequency tunable transpons. For example, you can see the flux lines here in yellow, and the green squares are our transpons with junctions right here where it interacts with the flux line, or squids actually, to make them flux tunable. And you can see that the 2 transpons are coupled quite strongly together. So we have measured a G of around 200 megahertz. And what we can do with these flux lines is that we can bring these 2 transpons into resonance with each other, which you can see in this plot. And yeah, there's a very clear avoided crossing here between the 2 transpons, which indicates that we are on resonance. And what that results in is that there is a splitting of the energy levels, giving a rest basis, which you see here. So we have the ground state followed by the A and S states, which is just a superposition of 0, 1 and 1, 0 in 2 different ways. We also have some higher order transitions that will be important in this experiment later on, but we'll come to that. Okay. Yeah, and a very peculiar thing that you might notice here is that we have these 2 coupled waveguides in blue and red that are coupled in a very specific way to these 2 transpons. And this is a device that we have had in our lab for quite some time now, and we have done many experiments with it. And the idea behind this is that we want to couple the specific A and A states of our system to independent waveguides. So for example, symmetry preserving transitions in our device are coupled into the blue waveguide on the right. So for example, you have here the transition from 0 to S, or the transition from A to 2 minus. So if you go from blue to blue, or sorry, red to red, you have a symmetry preserving transition, and this is then coupled into the blue waveguide. On the other hand, if you have a symmetry inverting transition, so for example, say from 0 to A here, or for example from S to 2 minus, where you are flipping the color of the transition, then what you have is that transition couples into the red waveguide on the left. Yeah. So let's take a look at some of these higher transitions that I promised. What we do is we activate a drive from the state S to the state 2 minus, which is one of the higher second order transitions. And then we let it decay at a rate gamma from the state 2 minus to the state A. And the state A is long lived, as we'll see later. To get to an impedance matched lambda system, we'll have to go to the rotating frame instead to see what's happening. And what happens is this drive brings S and 2 minus into resonance with each other, creating a lambda system between 0, S, and A, as you see here on the right. Now these 2 will have decay rates gamma 1 and gamma 2, which are dependent on the decay rate of S to 0, the decay rate of 2 minus to A, and the drive frequency omega. At a certain drive frequency omega, it is possible to equalize gamma 1 and gamma 2, thus giving us a impedance matched lambda system. Okay. So yeah, we have our familiar figure here now on the bottom left, and let's take a look at some of the data from our device. So what we are plotting here is on the x-axis is the frequency, where we do a simple spectroscopy of the S mode, or the S state of our device. And on the y-axis here, we have the drive power of this omega, which is in dBm as sent from room temperature. And what we are measuring is the normalized reflectance in dB of that transition. And what we see here as we increase the drive power on the y-axis is that at a certain point, you have a deepening of the resonator or the qubit or the S mode spectra, which indicates that we have introduced another loss channel into the system that is removing population from that mode. And to see it more clearly, we have a few line cuts. So the blue plot on the top here is at low power of the drive, so where the drive is effectively not doing anything to the mode, where you see this dip. But if we go to a higher drive power of around 7 dBm here, what you see is that the dip is much lower, indicating that there is an additional loss channel in the system, which is removing population. All right. So yeah, let's go back to the device because this does not reveal the entire picture of it. So let's zoom out a bit to see what's happening. So we still have our two familiar flux lines, but on the left, on the right, where I spoke about waveguides before, what we actually have is a readout resonator here, allowing us to read out the state of the antisymmetric mode, and a Purcell filter on the right, which prevents the decay of the antisymmetric mode into this waveguide or transmission line here. So yeah, this enables us to have a very long-lived A state that would help to read it out efficiently. So for example, here we have a example T1 of that mode, which is around 21 microseconds, enabled by these two filters on either side. Yeah, in summary, we have demonstrated an impedance matched lambda system in our device. And with this, we hope to do single photon detection in the microwave regime. The idea next is to calibrate some detection metrics for this device, which is the detection efficiency, the dark count rate, and the dead time of the detector. Then we would like to implement real-time photo detection using continuous single-shot readout of the antisymmetric mode or the A state, which will allow us to see quantum jumps of the A state, revealing the presence of photons. And at the end, we would potentially discuss some applications that we could do with this device. Yeah, thank you.
All right, thank you for that great talk. We have time for one question.
Yeah, thank you. Nice talk. So when you say continuous readout, don't you need to reset your lambda system?
Yeah, we would need to reset our lambda system. You're right. This is, okay, two things. This could be done in principle by switching on a drive on the A to S transition. So that's doing the same process reverse, emitting it the other way. But the thing with this device is we can optimize the T1 of the device also to make it slightly lower and optimize between the readout and the reset. So it gets resetted automatically.
Mm-hmm. So you have some amount of dead time for the readout.
Yeah.
Okay.
Yeah.
Thank you.
Thank you.
Okay, let's thank the speaker one more time.
Thank you.